All right, before we get into stuff about the tests, right. So because of tests, as I mentioned before, but make sure class this Wednesday. Then a couple tips about homework problems that are going on. All right, so for lesson, make sure I get these numbers right. Lesson 23, number 3. Yesterday back and forth is wrong. Because numbers jump a little bit, so if you find it a discrepancy, then it's actually a good thing in this case. And in lesson 24, number 1, trying to show that the solution to one wave equation after differentiating with respect to t is the solution of another wave equation. Use the Lembert's solution formula. Solve in the problem statement is the second problem, and that gets you on the path to getting a solution of the first one. Okay. All right. Because the problem is defined on the entire real number line, no boundary conditions, so the Lembert's formula applies in that situation. Okay. Now, form a test. 8 problems. I have to do all of them if you're a graduate student, 7 of the 8 if you're undergraduate. So basically here are the topics that the 8 problems cover. I mean, you can tell from a practice test, but just to confirm. So this will tell you where you want to look in the notes for any tips on how to work out these problems as they come. And so the first 4 problems will concern the wave equation in some form. Then 12 problems where you're solving some form of a heat equation. That can involve a source term. And then method characteristics of so first order PDEs, linear and nonlinear, and problem 7 and 8. Okay. So to be more specific, as we get into our practice problems. So the first one, you're looking at using the Lambert solution formula. Now, even though this is not an in-class test, a throwback to when I wouldn't give in-class tests pre-COVID. I will have a page at the end of the test that has called possibly useful formulas. So certain formulas are put there just for convenience, as opposed to sifting through a notes form. And then this is one of them, the Lembert's formula. Okay, second one, semi-impedance training. So you have a boundary condition to deal with. That's what's covered in lesson 18. So the Lembert's formula by itself doesn't work, but a variation of it does. Third problem, also wave equation, but this time on a finite interval. So what was covered in lesson 20 for a finite vibrating string is how to use separation of variables to solve a wave equation, just like for heat equation. Now, Later we deal with the finite Fourier transform. For a problem like this that has homogeneous boundary conditions, the two methods are actually equivalent. So you can use whatever approach you prefer. I'm just saying that if it's 0 less than 20 on the separation of variables for wave equation is specifically geared to this kind of problem. And certainly gives you what you need. For instance, we use formulas for the coefficients, Fourier series coefficients that play a role in the solution. For a problem, free space wave equation, it could be either 2D or 3D. So the appropriate version of Kirchhoff's formula is used in that case. And those are given in the list of formulas. The finite Fourier transform, this is for a heat equation. So you take the finite Fourier transform, the appropriate one, sine or cosine, depending on the boundary conditions. So in this case, cosine. You apply the appropriate transform to the PDE and to the initial condition, and that will give you this family of ODEs, and the transform of the initial condition will give you the initial values of those ODEs. Once you solve those ODEs, you apply the appropriate inverse transform. So the Cn of t if it's cosine or Sn of t if it's sine, those time-dependent coefficients are filled in to the formula for the inverse transform, and then you have your solution. Yes?
Can you show how you got the like the e to the power of -2 over 2?
Okay. Okay, here. All right. So what happens is, so here are ODEs in general for all n in this problem. Okay. Oh. Hold on a second. Hold on, I'm working something in my head here. Okay. So, I want to add some notes to this to answer your question. So in general, the combination of x and of x, which in this case is cosine n pi x over L for Neumann boundary conditions. And sine n pi x over L for Dirichlet type 1 boundary conditions. Now, in this case, if the initial data being cosine of x, my eigenfunctions here are cosine, okay, n pi x over 2 pi, because L is 2 pi in this case. In other words, so in this case, this problem, x n of x, equals cosine of nx over 2, where n equals 0, 1, 2, so on. All right. So you need to find the value of n, or it could be values of n, that conform that conforms to the initial data. In this case, plain old cosine x. Well, to get cosine x out of this, you need n equal 2. So that's why only for n equal 2 do we have a non-zero initial value. So for this ODE, so the general solution of this ODE, okay, so I'll fill that in here too. For CNT is CNT is equal to e to the minus n over 2 squared t Cn of 0. For this problem, all of these initial values are 0, except for n equals 2. So I'm not sure if I hit your question.
I still don't know how you got the exponent. How did you get it to exponent form? Is it because we solved for the eigenfunction value? Or?
Okay, so are you talking about sort of this?
No, just the e, like the e to the power of that part. Because I know where we got the n equals 2, but I don't know how we got to the part, why do we put it in that formula?
Okay. Oh, so really it's about the solution of this ODE. Okay. So what we have here, this is a here we have a separable first order ODE. So okay. Okay, so solution of the, so if I make it a little more general, I like y over prime ky is y of t it's that.
Okay.
Actually, even though it's not needed in this problem, it may be needed in a later problem. I'll add a source term. I'll call it b of t. So in this case, there will be an additional term. Okay. So if the PDE is not homogeneous, there would be a source term here, and you would need to take the appropriate finite Fourier transform of the source term, which would lead to a source term in your ODEs. So this full solution formula would apply. But otherwise, it's just this. Is that cover it? Okay. All right. Superposition, really you're breaking down the problems where the source term goes into one of the problems, the initial data goes into a different problem. I mean, you solve the two separately, you can add the solutions together. What ends up happening is when you separate them like that, and if you're using a finite Fourier transform, or whatever approach you prefer to solve the individual problems, when you get these ODEs, you may have a non-zero source term, or you may have a non-zero initial value, but not both. So that way the solution of each ODE is simplified a little bit. So like in this case, for first problem, we have 0 initial data for all the problems, for all the ODEs for first problem. In one case, we have a non-zero source term. But then for the second problem that we solve, all of our ODEs are homogeneous. So we have different solution formulas. So now that I've written this out here, we use different parts of the solution formula in each case. So for this problem 6, from a grading standpoint, I would look at what do you do for the 2 problems individually. In other words, chance to earn partial credit before you put it all together. Last problems concern reference characteristics. So for the first one, that would be a linear problem like this one, where you solve your ODEs for x and t. Initial condition, where initial condition is defined, describes the initial values for those ODEs. So you can solve these 2 first. And then you have the ODE for u, that you solve last. When you solve this, which brings you here, you have a solution in terms of wrong variables, s and tau. But then you use these, here you have x and t in terms of s and tau. So you reverse them. You want to express tau and s in terms of x and t. And you can fill those in here to get your final solution, u of xt. And then for the last problem, which is in terms of quasi-linear, first order PDE. So you still apply method characteristics, but it turns out to be easier to solve this equation first. And then that can, and then you go back and solve these. Because here, this equation, dx ds is equal to u. Well, u is a function of s and tau. In general, a very difficult equation to solve. But if you go solve this, what you find is that u actually does not depend on s at all, thus making this ODE easier. So this is the difference between a quasi-linear, nonlinear PDE, like in this problem, compared to a linear problem, number 7. Number 7, the ODEs for x and t will not depend in any way on u. So you can just go ahead and solve them first. But when it's nonlinear, these ODEs can depend on u. So you want to solve this first. And in this case, you're not going to have an explicit formula. Don't expect to get an explicit formula u of xt equals something. It can be implicit, such as what we have here. You have u on both sides of the equation. That's okay. You're not expected to rearrange it, solve for u, because in general you can't. And then don't forget the last part of the question, equation of characteristic curves. Now, so any questions on any problem on this test?
Where does the formula for number 6 u n t come from?
Okay. Okay, you mean?
I mean, just u n t, like the u1 x of t summation.
this,
No, I'm talking about just UN of t.
un of t.
Yeah, or u in prime of that t.
Okay, oh, these ODEs? Like,
Yeah.
Okay. So, what happens is, when you take the finite Fourier transform of this PDE, the left side will give you un prime. The right side will give you this, from transforming the UXX. Now, more, okay.
Oh, I see. I was trying to put the finite Fourier transform on both, but just the.
Well, yeah,
That's what
you
my
do.
was on the
You do. Now, okay. So what will happen is, for the UXX, I suggest referring to the notes for lesson 25. That's why I put all the which notes to look at the top of this document. That has all the rules for transforming UXX, whether it's sine or cosine, because the boundary values come into play. So that will tell you what the right side of your ODE is. And now in this case, there was no coefficient, like an alpha squared. If there's a coefficient, don't forget it. Okay, so that's where the ODE comes from. Now here, the interval is 0 to 1. In general, you're going to have n pi over L. But that's in those formulas. The formulas in the notes are for most general case. So definitely use them. Okay. Now, if you were just asking about where the ODEs come from, or
Basically that, but I mean, I figured that it came from lesson 25, but
Yeah.
I guess my issue comes with like putting them together, like doing them separately and then putting them together. Like I know that's the whole point, but
or you mean like solvent of the superposition part, or
yeah.
Admittedly, superposition doesn't give you much because you're solving two problems that are very similar. And the heart of superposition comes from something that I got into earlier. Oh, yeah. Because once you have those ODEs for un prime of t, you're going to use this solution formula to solve them. That's why I included lesson 9 in my list. That's where those formulas are, or this solution formula. So if you have a PDE that has a source term and it has non-zero initial data, okay, you assign the source term to one of your two problems, and that's where your solution formula for un of t involves the integral. And then for the other problem, gets the initial data, and your solution formula for un of t involves this. And yeah, there's nothing to stop you from just keeping it as one problem and doing it all. But so the superposition just lets you handle one piece at a time.
It's making it easier for me. I just want to do it the hard. But it's fine.
I'd expect nothing less from you. Sorry. Okay, but if you want to know what superposition does for you or to you, depending how you look at it, it's nothing more than breaking this down. Because the mechanics of how you solve the two problems, other than that, exactly the same. Other questions?
Can we go over number 20, lesson 26, number 2?
Lesson 26, number 2. Okay. Okay, redo my sharing here. Okay. All right. Okay, lesson 26. Oh, this problem right here? Okay. Okay, so the approach that you take is actually similar to what is described in problem 6 of the practice test. Where, okay, so you're going to solve a problem that's this, except only including the source term and not this. And then vice versa for your problem. And then.
But for the UT, it's a double.
Oh,
derivative.
Yeah, that's what I was
So-
wondering about. I don't know how to do like with
Right.
other stuff.
Okay, yeah, okay, so this is a wave equation. Okay, so as far as the, well, actually, what I said still applies, but now I need to give more information. Because if you do a finite Fourier transform, that part will still work out the same. You'd still transform both sets of initial data. Effectively, one of those is 0. The only difference, once you do all the transforming, is that now you have un double prime of t instead of un prime. So now you're solving a second order ODE. Instead of first order. And I have a problem here somewhere in the notes. Let me check which one. This one? Oh, actually I think it is this one. Let me check. Oh, yes, it is this one. Okay. So this illustrates what I was talking about. Because you have this source term here. Okay. So what happens is, yeah, here are your ODEs. And if I flip back to the problem that's given, okay. So what will happen here is your ODE will be very similar to what I'm showing you in the notes. I want that one. And that in one of these ODEs, you'll have a +1. Because your source term is plus sine, I think it's 3 pi x or something. Okay. So now, how do you solve these? So for a non-homogeneous one, here you follow this procedure. Here I use the method of undetermined coefficients that you would have seen in your ODE class. So here I've kind of given you a shortcut as to how undetermined coefficients plays out for a problem like this, where you have s double prime equals a constant times s plus a constant. Because if this constant was not here, then your general solution of this would be this. Having a +1 adds on a constant. So, let's see that. Okay. Now,
So in our case, the constant would be +3 with the a cosine.
actually, the 3 comes into play as far as which ODE it is. It's the ODE for n equals 3. Because it's plus plain old sine. In other words, the coefficient is 1. So it would again be a +1, but for a different n. Okay. Now, so what you would do is, Okay, so, alright, so in this case, because it'd be for n equals 3, that would affect these constants here, which would come from this constant here being different. So it'd be like minus and then 3 pi, but quantity squared. Okay. So then you substitute this form into the ODE, and then you solve for the unknown coefficients A, B, and C. So that's what was carried out here. Like, so in this case, for this problem, I substituted this in here, and when you, and the thing is, what you get on both sides is a function of t. So, and it has to be satisfied for all t. So that gives you a system of linear equations for the coefficients A, B, and C. So this turned out to be, in parentheses, turned out to be what A is. This was C, and B turned out to be 0. There's a reason why I did not put a problem of this kind in the test. So I don't know if that answers your question.
And the second part of the superposition would just be ut equals uxx without the sign.
Oh, okay. Whoops. All right, so one part of the superposition would only have this, have a sine 3 pi x, which would be but no initial data.
Okay.
And the other part of the superposition would have this, but no source term.
Okay.
Yeah, so there would only be one non-homogeneous ODE to solve. The first problem for n equals 3, and that ODE would have all 0 initial values. Other questions, whether they be about the test or more problems?
Can we do number 6 on lesson 25?
Oh, okay. Number 6, lesson 25?
Yeah.
Okay. All right. Okay, I don't know if there's a particular stage you want to ask about, or get started, or.
So I got to the like Sn plus n pi squared times like Sn, but I don't know how to get like the coefficients, I guess. Like,
Oh, coefficients of these?
yeah.
Okay.
It's like a non-homogeneous one. I don't think I've done one for yeah, I was confused.
Okay. So what you do is, when you're taking the finite sign transform, we go to the definition of that. Okay, you're using this. So in this case, the source term, that's what you're doing. You're taking the transform of the entire PDE. So you know how to handle that for UT and UXX. And now you take a finite sign transform of the source term also. And that's where this formula would apply. Now, that's what you do in general. In this case, the source term is, what was it, sine 3 pi x? Or
Yeah, sine 3 pi.
okay, so because your functions here, the domain is 0 or 1, correct? Yeah, so the function you have here is sine n pi x. If your source term is already a linear combination of those functions, then the transform is just the coefficients of those functions. Because you plug in sine 3 pi x in here, this integral is going to be 0 all the time, except when the indices match up. In which case, in this case, you get 1. And the same holds true for the initial condition. So what's going to happen is one of your ODEs for Sn will have a +1 added onto it. And if it seems like we're always getting +1s, it's because neither I nor the textbook author ever think to put in a term like this with a coefficient in front. Otherwise, that's what we'd have. But we're just being lazy.
Did you have to solve for ux of t first and then plug it into the integral?
Oh, no. Okay. This formula here is just how you take the finite sine transform of any function. So, in this case, since you're taking the transform of the entire PDE, okay, you handle ut and uxx according to those derivative rules. And then because that source term is sitting here, you got to take its transform also. And so that's what would go in here in place of u of xt. And then and then separately, you take the finite sine transform of the initial data, where that will go in place of this. Yeah. So, okay. Yeah, what I should have done is pointed you to this. This is the general definition of transforming any function.
Because in the lesson, you put f of x as equal to 1, and that's like, is that just like how you just do all of them, or is it?
Oh, sorry, what?
Or in the lesson, you had f of x equals 1, and that's how we solve for it, but like I don't know what to put in for like other examples.
Oh, okay. Right, so if I go back to that. Okay, because that's just what the initial data was.
But there's like another example like further down a little bit, where we actually set f of x equal to 1.
Oh, wait.
I think there
In here?
was either, I think it was a bit above, I think.
I figured this is what you're referring to.
I thought there was another example.
Well, okay, up here, I am taking a transform.
Yeah.
Yeah, that one.
Okay, yeah, so here I'm using that exact definition, applied to 1. But you would take whatever function you were given as a source term or initial data and fill that in here.
And for number 6, that source term would just be sine pi x, or would,
Okay, so back to the homework problem.
yeah.
Okay, sine 3 pi x to handle the source term that goes in the ODE, but also sine pi x as to get the initial value for a different ODE.
Okay, two twice, or
Yeah.
multiple times.
Yeah, so in this case, you're only going to have 2 ODEs of interest. One with the source term, one with the initial value. And everything else will be 0. Other questions about anything? the test, I will make it due Friday 11:59, like before. But I will try to put it out sometime by like tomorrow evening. All right, I'll stick around in case anyone has any visual questions, but otherwise.